All right. Welcome everybody to this webinar. We are very happy today to have you here to discuss about design for packaging. When we talk about design, of course, we refer to the design of photonic integrated circuits. We will demonstrate how to use the PHIX ADK, so the PHIX assembly design kit, to design photonic integrated circuits which are ready for assembly for applications in LiDAR and Datacom. So today we have with us two speakers. The first one is Andrea Alippi. He's a product manager at PHIX Photonics Assembly. He has a master's degree at Politecnico di Milano in engineering, and he spent 10 years in the packaging world. So he's very well suited to introduce you to everything PHIX has to offer. And then we have Craig Godbold from Luceda Photonics. Craig is an application engineer at Luceda Photonics. After he has a bachelor in physics and a master in photonics, and after spending several years working in telecom, he returned to photonics at Luceda to work as an application engineer. So the schedule for today will be the following. So after this introduction, Andrea will take the virtual mic and give you an introduction to PHIX and the PHIX characterization package to show you what PHIX has to offer. And then Craig, after introducing you to Luceda Photonics and our design platform, we show you how you can use Luceda software to design photonic integrated circuits ready for assembly for the PHIX characterization package. So using the assembly design kit that we have developed with PHIX. At the end, there will be a Q&A session. So if you have any questions, even during the talks, you can write them in the chat and then we can pick them up at the end. Or you can also keep them for the end of the talks and ask by unmuting yourself. Before we get started, I want to do a quick advertisement that we are always looking for people. We are hiring. We have a new role open for Luceda Academy Coordinator, but we are always looking also for software engineer and application engineer. So if you're looking for a job, feel free to reach out to me on LinkedIn or by sending me an email. And this being said, I will then stop sharing my screen and let Andrea take over.
So, let me share here. First of all, welcome everybody and thank you for the time for joining this webinar. Do you see my slides now?
Yes. Yes, I can see them.
Perfect. Okay, so for my part of the webinar, I will first introduce PHIX, so a little bit in details where we are and where we want to go. We will also go through clear details on the packaging side, design-wise, and then at the end some examples on best practices, what to do and what not to do when you are designing photonic ICs. So PHIX, we are a packaging foundry for photonic ICs and MEMS. So we don't manufacture the PIC themselves, but we package them, we assemble them, and make them into products. We are operational now since around 6 years, and we are based in the Netherlands, in Enschede, close to the German border on the east side. Finally, we are almost ready to go to our own building, which will have a lot of added value for us. We'll have a lot of clean room and rooms for offices to establish our 50 employees, 6 years, and see ourselves in the value chain. typically there is a customer with an idea, and then this needs to be brought into a
Yeah, and Andrea seems, okay, I think we lost him. Andrea, you were breaking up a bit and we lost your screen now.
I also had it before when you had your presentation, but
it seems other people in the chat are saying the audio is breaking up for them as well.
Yeah, it's breaking up for me also.
Okay. Still you don't hear properly?
We can hear you now.
Seems fine, and I can see your screen.
Shall I continue? Hopefully.
Yeah, go on.
Yes. Okay. So we have an idea from a customer, needs to be brought into a design of a photonic integrated circuits, and then there is typically manufacturing of it, and then that's where we play a role in the packaging and then testing of this. Typically it comes to customers, and they need to be further integrated into systems, or and then brought to the market. So we see a consistent added value to address the PIC design and the product design at the same time during the development. And this can, in our opinion, and also proved by development done like this in the past, to high performance and cost-effective packaging. At this point, we also look at the process, the assembly process development, and also the equipment development. We serve many type of customers, and from a very small volume and full of packages, characterization packages typically, where the technology just needs to be tested and verified, scale and drive these through volume production up to hundreds of thousands of modules. We also provide contract manufacturing, typically when a customer already knows what they want, and they just want to use our fab to establish the manufacturing. We have a portfolio at our stock in terms of both closed boxes and open packaging packages, and we can use them for small volumes up to higher volume for this. We also provide engineering support. We see typically required for a customer that they are not acquainted yet on packaging, so they need to get some guidance from us, especially in the design phase of their PICs, but also through the products perspective, and then we are able to scale this to the volume required. This is an example of maybe our core expertise, which is in hybrid integration. As you may know, there are available many technology on the market, PIC technologies, but not one of them excels in all the specification. For example, the indium phosphide is great for light generation and amplification, silicon nitride, low loss propagation, and silicon photonics has the advantage of the CMOS compatibility in the foundries. One way is to combine all these at the chip level and create products that excel in performance, combining all these PIC technologies. To conclude on the introduction to PHIX, that's a little bit our way on approaching challenges and problem solving. We look to optimize design and cost, and then looking through the product design, the assembly process, and the equipment at the same time. Now we can go a little bit deeper into design for packaging. Again, I would like to start a little bit on the higher level to provide some motivation for the need of standardization, and also the way that we see that we have already let's say pursue to achieve the scalability that is required for the PIC technology. This also serves as an introduction to our PHIX characterization package, because how did we reach that point is that we try to find a trade-off between performance, cost, and lead time. So that's a little bit the outcome of this first step of standardization. More detail in the next slide, but I would like here to maybe introduce some differences in terms of design styles. For example, we see many design for testing developed in the past that, in our opinion, should move more into design for packaging, for manufacturing. To make an example here, so we see a lot of, for example, small dies with electrical and optical I/O disseminated on the PICs. This is great if needs to be addressed on a testing level, maybe even wafer testing level. Then a lot of feature can be implemented in the chip, in the wafer, and then it's a cost-effective solution. This is not, in our opinion, the best way for manufacturing, because there is often a trade-off between die size, amount of interconnects, their position, and design of the PIC. So we try to standardize in this way, and we believe also that to achieve this good design for manufacturing level, design rules are essential to drive standardization and enable scalability of this PIC technology. Another concept is the first design right. I would like to introduce this from a packaging perspective, because of course the first step is to get a first design right at the design houses, at the software houses, and at the foundry in terms of yield and manufacturing yield. But what we see is a requirement also to iterate on this design on the packaging level. This is important because sometimes only after everything is packaged, everything can be tested at the same time, becomes clear. Maybe a parameter needs to be optimized. And then with our characterization package, we manage, in our opinion, to provide a solution that can iterate at the cost-effective and competitive lead time. How do we achieve this? We have already worked many years in the past with early engagement with customers and foundry. So education really on the design, when the design was becoming real, and then we can of course intercept and provide our guidance. We don't see this to be the scalable solution. We need to be involved with design software houses, and that's the reason why we have this development with Luceda to get this ADK finally at the first step of a customer or a designer. Okay, now it's time a little bit to go on the characterization package in detail. So this is a modular packaging platform which consists of a mechanical base, typically gold-plated copper material. This serves as a great thermally stable support for the photonics. It can be controlled with the Peltier element, which we also provide optionally, so that you can have a feeling on the temperature control of your photonic circuits. We have some certain range of PIC sizes that are supported here, and a range from 4 to 20 millimeter with different combination possible. And in regards of the electrical and optical I/O, we can here support up to 64 optical fibers and 120 DC electrical connection. So this is a DC only package. We have an option to support both edge and grating coupling interfacing technologies. And at the moment, we have a wavelength targeting at 1550. We are considering to expand the standardization to 1310 as well. And both single mode and PM fiber are supported. About the electrical, I mentioned 120 DC. We have 2 separated PCB with 60 separated connection, and they can be easily interfaced with the fan-out board that we also provide off the shelf. Going a little bit more into the details of the PIC design, here the example has been given with the edge coupling interfacing method. So we have typically east and west the optical edges, and north and south the electrical edges. You will have predefined areas to allocate optical and electrical IOs with the relative keep-out zones, and this is what you will get with an ADK. The minimum pitch on the bond pads that we can serve here is 150 micron, and that's a standard for us. Bigger, it's always possible because we can fit, we can just wire bond whenever it's needed. A finer pitch, it's possible, but needs to be checked on the engineering side. A little bit more details on some highlights for design guidelines. For the optical alignment of fiber array to chip, in general, we exploit alignment loops. We require 2 of them for edge couplers, and 1 of them is needed for grating couplers. Why do we need this? So a couple of reasons, because we can be insensitive to the PIC design with alignment. We can also learn during assembly in separated batch the performance of your edge couplers, because we log the data of the loops, so we can learn coupling loss and propagation loss. And our stages are configured for this, so we can assemble with 6 degrees of freedom. Another highlight on keep-out zones. Here you see quite sensitive, quite safe numbers, which will eventually increase the die size. These are very safe, as I said. If you manage to design the chip like this, we can assemble without any constraint in our tools, in our processes. Of course, smaller numbers are possible to have more compact chips. In this case, we will need to have a check-in engineer. Another comment about polishing. Polishing is typically required to optimize the coupling efficiency of edge couplers. Not all technology requires this step, but if it is required, we have established a polishing ruler where we can set the target during polishing and the tolerance that we can achieve with our processes. If you have a look to our website, you will find a lot of documentation, some more technical than others, flyers, and white papers. Here I have a look to the design rules, because we have 2 main documents and they have some differences between each other. The PHIX Characterization package design rules basically describes the package that I discussed now in the last slides. Of course, in the document, there are all kinds of additional details important for designing. We have another document, which is the design guidelines, which is a much more general document. Here we addressed also other domain, for example, high-speed RF or hybrid integration, chip-to-chip assembly. Also interesting would be all the package types, basically our portfolio of packages that we have on stock. I'd like to spend a couple of more words about the differences between these 2 design documents. In general, when you follow the design guidelines, the general document, the chip can be assembled at our site safely. This doesn't mean that directly can be packaged into the characterization package, exploiting, for example, off-the-shelf BOM assembly processes and very short lead times. With this, I would like to explain with an example. For example, you have an RF requirement. We had a lot of experience in this in the past years. Many customers, many products developed with an RF requirement, high speed. So typically, and so far, that's what always happened. This turns directly into a custom product. You need to minimize the wire bond length. You need to optimize some other parameters, and performance are the most important thing there. At the same time, because we have worked on so many different design, we also see some similarity in this. So we are working at the moment, and hopefully will be released within this year, to the second iteration on the characterization package. This will support RF. Just some outlook here on how we look into. The design on the PIC will be slightly different. There will be only one optical edge, let's say on the east side. Opposite to this, there will be the RF side connection, and then north and south will remain DC. On the right side here, you can see the current status. It will not be, as the DC characterization package, a full off-the-shelf BOM, at least not in the first iteration. We will have maybe 80% of the BOM on stock, and there will be something that will be optimized for the application. Now we can go to some, let's say, lesson learned that we did together with our customer in the past. So some advice on what not to do and some reason behind that. We said optical east-west and electrical north-south. This would be ideal for any design, not only for the standard packaging scenario, but also for slightly custom, maybe with finer pitch or additional requirements. Of course, everything is possible, but we try to really limit the differences to minimize the development cycles also at our side. Wire bonding, of course, here also exotic wire bond schemes, bond pads everywhere on the chip. If possible, please try to align these to the edges of the chip so that will not only turn into a much more, let's say, an easier job, package robustness of the product in the end. The alignment loops, as mentioned, are important features for us. We can also package, and we did in the past without alignment loops, but it requires additional effort at our side. We can use free space or fiber probes, but if possible, alignment loops would make our life easier, definitely. Shipping, of course, sometimes underestimated. It's not only getting the chip package, but also getting it safe to the customer. If you will ever order a characterization package from us, you will get a shipping box with the validated method associated and functional. With this, I will close my presentation. You can see some more or less customized products assembled at PHIX. Many of these did require quite an effort at our side because this is sometimes painful. We are working to turn this into more standardized solution to drive down cost and time to market, keeping a look to performance, of course. We believe this will be possible, implementing more and more standardization in the PIC for packaging, PIC design for packaging.
Thank you, Andrea. This was very interesting.
I hope my sharing did go well after.
Yes, there were only a couple of moments here and there, but overall the audio was good. There is a question in the chat from Dan Pitt from Excelprint. to please say more about what should be standardized. I think you covered some of the main standardization issues, but if there is anything else you want to like highlight or talk about.
Yes, so we see levels of standardization. So it really depends also on the application that you're working on and really what you want to try to achieve. The first level of standardization is probably what you see in this slide. That's the first level, because if you design like this, we will be able to package. But yeah, I cannot really say if this is everything that you want to integrate in your PIC. So it depends. It depends a little bit on what you're trying to achieve. I would say this would be the first step.
There is also another question from Samuel about, he's asking, is there a recommended scheme about how to place signal and ground bond pads?
So this is a high-speed RF question, I guess, if I need to judge signal and ground. Yes, so if you have a look to this document, so the PHIX design guidelines, there are some guidelines about RF packaging. If I recall correctly, 500 micron pitch was the signal to signal requirement, but it eventually it really depends of which foundry you are working on, because some foundry they have fixed patterns, and that's why up to now most of our RF design were custom. We are happy to help in the design phase, so I can leave my email in the chat. So for anyone specific question to design, we are happy to support.
Thank you again, Andrea. There will be more time for questions at the end if any more come up.
Sure.
We can give the virtual mic to Craig, who will now introduce the design flow for design for assembly. So designing using the Luceda Photonics design platform and the PHIX ADK.
Okay, hello everyone. And you can hear me okay and see the screen?
I can see the screen and I can hear you.
Okay, great. So yes, and following on from Andrea's very nice presentation, I'm going to go over a couple of things. The first part of the presentation will be a general overview of Luceda, and the second part of the presentation will look at two design examples where we use this PHIX characterization package as part of our ADK. Click. Okay, so an overview of Luceda Photonics. As you can see from this map, we are a company with a global presence. Our head office is in Belgium, and we were born out of the Belgian photonics ecosystem 10 years ago this year. We also have an office in Shanghai. We have an official partner in the United States, Spark Photonics, and a reseller in Japan. And our company's vision is to help photonic IC designers enjoy the same first-time right experience as electronic designers, which is a noble vision, let's say. And the mission of the company is to accelerate the design team's time to market by creating a very powerful, flexible, and efficient design flow. And we are a company of photonics experts. It's a pure photonics company. So looking at this, our first time right experience, how do we do that? And we do this by using our PHIX design platform, where we try to capture the entire design flow in our integrated platform, from component design, circuit design, design validation, simulation, up to submitting a GDS for fabrication. How we work, so we focus on parametric design principles. We use Python as our standard language. It's a very well-known language. And so the idea is to design your PICs, your model libraries, and all of your IP management in this centralized platform. This helps reduce design errors. It enables the designer to simulate parametrically, which reduces design errors. And we provide a lot of PDKs for our users. So we have around 30 PDKs currently, and also now ADKs and TDKs. And so all of this together helps to improve the time to market. I mentioned the PDKs and ADKs and TDKs. Here is an example of the design kits that we offer. You can see them by the different materials that you would work in. And of course, assembly and testing, which is something we've recently started to develop more. So looking a little bit at the design flow that you could work with in PHIX, you could start with a component. So you start with the standard language of Python. You can create a parametric layout and simulate your component. And you can do a virtual fabrication of your component to get a good 2D view of the component. We have our own EME simulation tool, but we also have links with third-party tools like Numerical. So it's a module that you can use to export your designs for full FDTD simulation. Then you can look at circuit design, which is something we're very good at in particular. Again, it's a code-driven approach, which we have smart optical and electrical routing, which you can see here on the right, which enables easy connection. We also have a tight link between layout and simulation, which makes it easy for designers to iterate their designs very quickly. You can quickly change a parameter and view the layouts and simulation side by side. And we also recently added a schematic capture tool, which enables a user to start a design from a GUI, let's say, and you can generate code from this schematic tool. I mentioned the tight link between layout and simulation, and you can see that here on the right. We have an example of a splitter tree. And by creating a parametric design, you can very quickly change a parameter and rerun your simulations and view them side by side. We have our circuit simulator, Café, which is a very fast circuit simulator, which allows for frequency and time domain simulations. And of course, you can then easily communicate all of your designs using our schematic tool. You can validate your designs. So with our PHIX canvas, you can verify the optical and electrical connectivity. You can open up the components and view all of the parameters and modify them if you wish. You can do a netlist extraction in both optical and electrical. And you can then simulate post layouts with Café to verify your design. We also help with tape out preparation. Of course, this is very important because in the end, you want to manufacture a PIC. And so we provide means within our software to address some of the most common issues that you would face with tape outs. So for example, a snapping error, acute angle patching. So we have tools in our software to address these issues. And then in the end, you can export to GDS. We also offer extensive training and support. We offer onboarding trainings, and we have a very detailed academy, which we are always working on to provide new and interesting examples for our users. And we have a very strong support team of photonics engineers to support the designers every step of the way. So that's an overview of Luceda and how we work. And so now we're going to look at designing two devices using the PHIX ADK. Now, I'm going to tell a little story about designing. to illustrate this point. So we start with a photonics engineer, Eva. She's a highly skilled photonics engineer, and she works at a space company, and she designs PICs for satellites. And her boss comes along and says, hey, Eva, design us a chip that will detect neutron stars. Okay. So Eva starts implementing her design. She uses some foundry building blocks. She uses the company's own IP, and she creates a design. And this is then submitted for fabrication. In the meantime, though, she decides to leave the company, and along comes Dennis to pick up this project. So the chip is fabricated, the chip is measured, and this can take anywhere from a few months to maybe a year. But then there's a problem. The results are not good, and something needs to change. Okay, so the boss says, please change the design. But Dennis has an issue because the person that made the design has left, and he doesn't know how to run the simulations. He's not sure of the design rules, and there's a deadline coming up. He also then realizes that the design doesn't take into account packaging and assembly. And so now he's in real trouble. And we see that the design flow has increased in time significantly to reach the packaged product. And this is not a unique story. It's easy to end up in a situation like this for a designer. You may not see the full road ahead. And this is what we are trying to do with our software, to make life as easy as possible for a designer. And so packaging a PIC, Andrea covered this in a lot more detail. So this just summarizes it quickly again, the key ideas. You have your photonic chip, but you also have packaging concerns. For example, your electrical interfaces, your BOM pads, north or south, you may have your optical interfaces at each side, east and west. And so the concern for packaging would be the positioning, the pitch, the number of pads, whether it's RF or DC, and then of course thermal and mechanical issues. An assembly design kit, which we've implemented with PHIX, this is needed when a packaging company provides a packaging or assembly solution to another company that designs photonic chips. And this assembly solution requires the chip design to comply with particular rules and boundary conditions to make sure the assembly is successful. What's great about this in our software, we have our PHIX ADK here, but you have many possible combinations as a designer with which PDK you want to use. So up here you see from SciFab. SciFab is just a demonstration PDK that we use for Luceda. But of course, if you're designing something with a foundry in mind, you can use another design kit that's in our software and then combine it with the PHIX ADK to create your design. So you might start with your PDK, you build a library and a design, then you iterate to a second design and a third design, and then you bring in the ADK and the TDK to validate that this design is compatible with the full process from fabrication up to assembly and testing. So let's look at a more concrete example. The first example we will look at is an optical phased array. And this example is going to use the PHIX Characterization package, the DC package that Andrea talked about at in his presentation. Just a quick overview, an OPA is an important photonic device used in a variety of applications. So you have an input light source, and by using phase shifters in the different waveguides with equal optical path lengths, you can steer a beam. And so a common application for this is LiDAR, or for example, free space optical communication, amongst others. IPIS, our design platform, is very well suited to design these type of OPAs because the user has simultaneous parametric control of the layout and simulation, which is very useful for a designer. These are very large but regular circuits, and this means that they scale very well. You can take a very simple design concept and very quickly scale it up. In our Luceda Academy, we actually have several examples available for our users, fully coded examples, so you can see how to implement an optical phase array and understand some of the technical details. So we're going to implement an example using the PHIX Characterization package, and this image here will be familiar from the previous presentation. So you see the epoxy area, the fiber array, the alignment loops, and then you also see the area where the bond pads can be positioned. To give you an idea of what it looks like in the code, you would simply import your PDK, whichever one you use, and then you would import PHIX, and then an OPA, which you've already designed. And then, of course, here is an example of the PHIX characterization package with some particular parameters of interest. This ADK available in our software will tell you specifically what you can and can't do. So it will define in the software what the options are for each of these parameters. If there are a select number of options, if there's a range of options. And so here we can see, for example, the space where we can place these bond pads. The alignment loop was already mentioned. This is a good part of the package. It allows you to, by maximizing the transmission in this loop, it helps to guarantee good alignment for the rest of the fibers in between. Now, a little bit more of the code. So to create a packaged OPA in IPCIS, you would have an OPA that you have designed. So here we're going to define that here. But as part of our package class, we will define a trace spacing, so the distance between electrical trace centers. We will also then define our frame, which is the PHIX package, and the type of coupler we're going to use. And then we instantiate this. To make the electrical connections in IPCIS is very easy. You see here at the bottom of the device, the bond pads, and then we need to connect these electrically to the heaters in the phase shifting waveguides. And so we can do that in a very simple way with this little section of code here, where we use the method i3.connectElectrical. And we can choose the frame and which direction of the frame and which channel of the frame. So that's a very nice way of routing because it's very intuitive. You define some angles, which will define where the routing takes place that completes the connections. And we've also implemented some control points, which will dictate how far you travel above the bond pads to clear this area. And then it will define a horizontal section and a vertical section. And the rest of the routing takes care of itself automatically. Here we see those electrical connections coming into the heaters. And this is the OPA itself. So you see here's the output fibers. And the optical path lengths are all equal. So from this input, whichever direction you take, you will always come to an output where you've traveled the same optical path length. And this makes then applying the voltages to the phase shifters an easier process. You can easily linearly increase the voltage to create a linear beam steering, for example. If you zoom in on this, you will see that the heaters are either side of the waveguide, so to keep the heating symmetrical. Finally, we just put this stuff together. We have the OPA. Here you see the bond pads with the electrical connections to the waveguides, and then the PHIX package. And so what we do is just place them. By using our specifications, we simply place the frame. Here we've chosen the origin of the coordinate system, and we place our OPA relative to this frame, where we can choose the OPA output 0, and we place it relative to a particular east port. So in this case, east into here. And then with a offset of 1500 microns, which would be this distance here. And then we do a connect Manhattan for the OPA in, which will connect to West 10. And we define a straight section here of 600. And so that just connects everything together nicely. And we get our packaged OPA. And we can visualize this by just running layout.visualize, and we can produce our GDS by using write GDS. And so this is a more standard example that uses the characterization package, the DC characterization package. But now we're going to look at a slightly more complicated example of an IQ modulator. So this is an RF design. And so in this design, we're going to still import the same package, but as Andrea mentioned, RF comes with a little bit more customization, and it's a package that's being worked on at PHIX. So why do we need this IQ modulator? Well, we'll start a little bit with electro-optic modulation. So if we're just sending high-speed electrical signals over a relatively short distance, you would need to regenerate that electrical signal as there are higher losses. But we can actually modulate an optical signal. So we take our data and we transfer it on an optical wave. And this eliminates the need for the same type of regeneration. Some types of modulation that are of interest here is amplitude and phase modulation. Here we see works only for amplitude modulation with the photodiode, but we want to take advantage of phase modulation, which gives lower insertion losses and a higher bandwidth. So this is where our Mach-Zehnder modulator will come in, because this allows us to convert phase modulated light into amplitude modulated light here using electro-optic phase modulation. Here you see two Mach-Zehnder modulators put together, and what we could do is use two input frequencies, but this isn't as efficient as it could be because we're using two signals. So we can combine this by using another splitter, and we have one input signal, and we split that into its in-phase and quadrature components. And doing this significantly increases the spectrum efficiency. So how can we create a layout of such a modulator? Again, it's quite similar to what we've seen before. We're going to use a PDK. We're just using the demonstration PDK from Luceda and our PHIX ADK. And we're going to create a class of an IQ modulator where we call some child properties of a splitter, a Mach-Zehnder modulator. And just to be clear that these have been designed in another file. We tried, it's good working practice to have a very hierarchical design where you don't put everything in one long file. And so we're going to import these into our class. And then we define some properties of spacing. And then here we define our default splitter for each modulator. We import our modulator and define our Mach-Zehnder modulator, our phase shifter waveguide, and then our heaters. And so this will create our IQ modulator, which is the combination of both Mach-Zehnder modulators. We then take that and pull that into our packaged IQ modulator. So that would be this DUT here. So we bring that into our package class with, again, these same properties of position. And then this time we bring in the fixed packaging frame. So we've now taken all of that functionality from the IQ modulator and packaged it in the fixed frame. I'll finish by looking at some simulation that you can do in IPCIS for this type of device. So I mentioned earlier on that CAFE, you can do time domain simulation. And so we will do that here to visualize a few different modulation schemes. So here we have our IQ modulator and we have a source input. And we have in-phase and quadrature signals and reverse signals, and also the heating applied for the in-phase and quadrature. And then we detect a probe to detect the modulated output. And so to do this, we have already provided some examples which are available in our Luceda Academy that define a simulation recipe for here simulate IQ modulator, and also for a 16 QAM case. And so then we simply create a simulation file where we define these parameters, and to select a different modulation format, we just need to apply particular voltages to either the in-phase or quadrature heaters and the different arms of the two Mach-Zehnder modulators. Here is one example. So we're going to use the simulate modulation QAM, which we would import into this simulation example. And then we simply select the voltages that will produce the 16 QAM. So here we're applying a voltage of pi to give a pi phase shift to the Mach-Zehnder left arm and right arm. So left arm 1 and right arm 1, as well as a voltage of half pi to the heater in phase. And it's just a simple case of modifying these to generate different modulation formats. So here we see PAM4. In this particular case, there's no phase modulation, so we're just modulating the different amplitudes. And here we see, again, a phase shifted, a quadrature phase shifted, or phase shift keying modulation, which is quite similar to the QAM case, but has a different application of the input signals. So this is an example of the type of simulation you can do in IPCIS. So you can simulate very high-speed signals and generate eye diagrams and constellation diagrams. So to conclude, you see here Dennis is not very happy because he didn't use IPCIS for his designs. And you see here a lengthy time scale to get to packaging, and after many design changes. However, the idea is that if you use IPCIS for your designs and you take into account all of these things from the start, fabrication, assembly, and testing as well, leveraging our software and our support, you can significantly cut this time down, which in the end saves a lot of effort and money. And you get to build a nice, clean and documented library. So in the case that people come and go, you can certainly keep track of the work that's been done and easily reiterate. So that brings me to the end of the presentation. And so if anybody has any questions, I will gladly take them.
Thank you, Craig. We already have a couple of questions from the chat. So we have a question from Juan, which is, as far as I understood, the north-south paths in the ADK are devoted to DC signals, but normally the IQ modulators would expect high-speed signals into the electro-optic phase modulator. Can these paths be also used for RF, or am I missing something important?
So for the RF pads, of course, they are different. And so it's important, the positioning of those pads, it does require a difference. So it's not the same as DC. What we've shown here is using as just an example of how you would implement the PHIX ADK. This characterization package is actually for DC. And so the RF design would require a little bit of customization from the PHIX side. And so, yes, this was to demonstrate how you would implement the PHIX ADK. The positioning of the bond pads is important. I'm not sure if I can quickly go back. So if you notice here, the bond pads were repositioned as close to the edge of this particular implementation of the package as possible, because that would be important for RF design. But yes, I'm not sure if that answers your question completely.
So maybe I can add something on this, because that's actually a great example of what is covered. So this design is covered by our general design guideline document, where it is something that can be packaged at PHIX, but is not currently fitting in the characterization package for DC. So eventually we will probably turn this design when we have this characterization package for RF. We will move the RF edge on the west side. We will leave one optical edge on the east, and DC will remain north and south.
Okay.
I think that is clear and makes sense. So indeed, the message here is design as standard as possible. And in this case, even when you're moving to RF, there are still some standard rules you can reuse from the characterization package and then add a bit of customization on top of that, which is required for RF. And of course, it will update the example once the RF package is released by PHIX. So we have another question from Thibaut. Is there any compatibility problem to use both a TDK and an ADK inside IPCs? Maybe I can take this question. There could be, because both TDKs and ADKs contain design guidelines, so with design rules about placement and distances between bond pads or grating couplers and so on. So it could be that a testing house has different rules compared to an assembly house. And so there could be some values, let's say, at the edges of the allowed range that are allowed in one place and not in another. So that is indeed a situation where it's still a bit complex to combine the two. But I think that we will make some steps forward in that. For example, like thinking about TDK, that we just released a testing design kit with VLC Photonics. I believe that VLC has talked with PHIX many times, also to discuss about this kind of requirements. I think that a TDK in principle is a little bit more flexible than ADK, where you have some more restrictions in terms of the package, while the measurement setup, I think, can adapt a little bit more. And you can probably find some sweet spots where you can follow guidelines from both.
Okay, thanks. And there's no problem to import both libraries in the, like not like two PDKs that you can import. You can import.
No, in principle, it's not a problem because so the reason why you can't use two PDKs at the same time is because they are based on different technologies, so different layer stack, while assembly design kits and testing design kits don't have a layer stack because you don't fabricate a chip using those. But a TDK will contain, for example, a frame for placing bond pads and grating couplers for testing, and then an ADK will have its own other frame for packaging. So, I mean, you can import them at the same time, but they have different cells when it comes to frames.
Yeah, but for layer and everything, I might be able to use it. Thanks.
Yeah, no problem. There was also another question from Ali. Can you make routing equal lengths in the code, and can you define areas, rooms defining where the route must be?
Maybe not rooms as such, but certainly if you're defining where the route must pass, we use control points. So you can choose particular coordinates where the routing must go. So you can bundle routes, for example, and then you can select particular coordinates that those connections must pass through. That enables you to traverse through complicated obstacles, let's say. And for our latest version of IPCIS, which was released today, we now have a electrical bundle routing, which enables you in even a more efficient way than I showed here to take multiple electrical connections. And with a very simple implementation, you can collectively route in a very complicated trajectory. But maybe it's not best to think of it as like a room where it exists. It's particular points that it must pass through. Maybe would be a better way of saying that.
And to answer to the first question, you can implement some, say, knowledge in your code, so some calculations to make sure that, for example, two arms of an MZI have equal lengths or are implemented with a certain length difference between them. And also, like, again, about the second question, to reiterate on what Craig said, we have some like very smart way of defining where routes should pass. And just today we released Luceda 3.12, which adds even more capabilities to our place and route engine, especially to define where routes should pass compared to other instances in your circuit. So you can very easily avoid components, or you can easily avoid certain areas, keep out areas in your chip, so that you can create rooms, let's say areas where your routing doesn't pass. We have another question from Luca. 2 questions. Is it possible to choose in advance which type of packaging to implement beyond the characterization package?
Is it possible to choose in advance which type of packaging to implement?
So I think,
or maybe Andrea, if you have a thought.
I think maybe this is more for me, but yes. If I interpret this correct, it's more about the type of packaging, the type of package. So maybe not a open package, it's correct. Then in terms of design guidelines, we don't have yet design rules for assembly into packages. So that's more something that we would do in a custom environment framework. But of course, we have experience to guide. So if anyone is working in that direction, I would kindly suggest to engage with us, and then we can help you directly on that. Eventually, on the long term, we will enable design rule also for packages. So even simple 14-pin butterfly for laser engine or more complicated ones, on the long term, they will need to be there, definitely. And second question, yeah, you can.
Yeah, to add on top of question 1, of course, once these packages are implemented by PHIX, we will add them to the ADK. For the time being, if you need to design for a custom package, that's something you can still do using the software and the ADK. You just don't use the custom package that we have already implemented, but you will need to modify it to make it custom. But it's still possible to control the whole flow through your design software, so that the moment you need to change something or adjust something, it's easy to do so. And yeah, to go to question 2, in the context of hybrid heterogeneous integration or design of PICs, will different design guidelines be implemented?
Yes. So we have already a starting point for this in our general design guideline document, where we have, for example, on one, we always use the same integration scheme. So optical edges opposite, east-west, and electrical north-south. But on the optical edges, you can have, for example, more components. You can have a fiber array, you can have a laser unit, and on the other side, you can have a modulator chip, a detector chip. We have design rules for this. Very simple. We need some space in between 2 adjacent components to enable hybrid integration, which, if I don't recall correctly, is something around 4 millimeters. But if you're working on that, I also suggest to have a look to the document, but engage with us directly on this, because there are a lot of experience that we can share on this.
Perfect, thank you. Are there any more questions? I don't see any more in the chat, so I think we can conclude. I want to thank Andrea and Craig again for presenting today. I think it was very interesting for me. I hope it was very interesting also for everybody who attended. Thank you so much for being here and for interacting with us through all your questions. And hopefully see you in the next webinar. We will soon announce a webinar for June, so stay tuned and see you next time.
Thank you for your time.
Yeah, thank you for your time, everybody.
Have a good evening.
Have a nice evening.
Thank you and good evening.
Bye-bye.
Good evening.